Hello guys, welcome back. So I have run the multiple sims that we've created together, and this is the dust hit. You can see we have some cool expansion there. The main thing that I'd like to fix is these mushrooms. I mean, they look nice from the top view, maybe even from this view, but I don't think they're realistic. So I'll probably lower the amount of velocity and add more noise to it to break this up. Also, with these type of effects, you generally get a trail behind, not so much velocity pushing outward. This is generally a trail left behind the object emitting that. So this is the first sim, and then I run the first sim as well that we created with the statue emitting the smoke, and with the temperature field I run it at a high res setting, and it took about 3 hours to sim to 100 frames. And this is just a couple of frames being previewed here. Cool, and then I run this as well at a high resolution, and I think it's very, very cool. Okay, so let's continue now. What we're going to do now is create some more smoke sims, and in this case we're going to create a smoke sim that we're not going to render by itself. We're going to use this smoke sim to drive the motion of particles. We can definitely render the smoke sim that we're going to create. It's going to be a high-res sim with all the details needed, but what I want to teach you guys is how to use that to drive particle sims to create interesting motion that are really hard to create using just particle sims. And the first thing that we're going to look at is how we can take a volume and move or advect points with it. And the process of moving points using a volume data is called advection. And we're going to learn how to do the advection at the SOLP level, and then do that in the POP solver in the simulation itself. And we're going to start by first looking at the let's first create some data to work with. So I'm going to create a box here, and I'm going to give it a velocity. Actually, the idea is we want to convert this box into a volume, and then add a velocity field to it. And then I'm going to use the volume trail, which we used already, to preview how this velocity looks like on points. So let's do all this. I'm going to create a VDB from polygons and convert this into a fog. I just need the volume data, and I'm going to create a velocity vector on these points and then generate a field from that. So v is equal set of just an up vector, velocity pointing upward, that's all. And then we're going to sample that in here by clicking the surface attribute plus sign and then type in val. That's the name of the field I want. And then I'm going to create a grid. Grid, and let's place that so that it covers this area. Cool. And I'm going to show you multiple things, hopefully teach you guys some cool stuff in SOPs as well. So let's scatter some points, and let's connect the first input, the second input, and let's preview the volume trail by selecting the velocity field. You can see it's pointing upward. Now it's very uniform. It doesn't have any variation. We can change it here, maybe 0.5. It's going to be aiming to a different direction. Now if we take a look at other nodes in Houdini, for example, we have what did we use? Let's take a look at the Voronoi fracture, which we're going to learn later, and the fluid source, which we're going to use as well. So these two guys are made of multiple nodes. And the way to know that is by right-clicking. You see this allow editing of content. If we turn that on, we can double-click and dive inside. I mean, we can double-click at any subnetwork, but it will be grayed out. If we do that, we can dive inside and edit them. And you can see all this. All these nodes are made of Houdini nodes. They're just networks inside of networks. but some other nodes are implemented in C++ or in Vex and compiled, and they don't have this allow editing. Okay, we can double click on them, and this is one of them. So we don't know how Houdini is doing this. And I want to show you guys how we can create our own version and how and explain the process of particle advection or point advection in SOPs first, so that we have a better grasp of the whole process. So let's create our own trailing node and see what's required to get this trail. Now, before I do that, I want to add some velocity randomization to the velocity field. So we're going to create a volume VOP and import the velocity field by using a bind node val, and this set to vector. And then I'm going to simply generate a noise, and let's add this noise to the velocity field. Okay, let's make sure it's a 3D noise, and let's bind export this. Cool. Okay, let's go up and let's take a look at the trail. See, now we have more, we have variation on the trails. And let's dive back in and increase the amount of noise we have here. 10. Cool. So now we're getting these cool curves. Now, how is this node doing that? Well, if we set the trail to something very, very short and view the points, we can see that it has a start point. And what Houdini is doing is using these points to find the velocity value from this volume and using that to apply an offset to the first point. But it doesn't override the first point, it adds a new one. Okay, so it's gonna take the original point, look up the velocity value in this field, say, okay, I have a point here, what is the velocity in that voxel? It gets that value, it offsets itself, but keeps a copy. Now we have a second point. The next time it's going to take the second point, this point here, do the same lookup and find a new velocity. And as we keep increasing this, you see it's going to continue expanding and traveling through the volume. And this process is called iteration, in this case, iteration or advection. We want to do the same thing. So let's see how we can, let's keep this in here. Let's see what is the easiest way for us to get these points and query where they are in the volume, what kind of velocity is in that voxel. And to do that, we're going to use a point VOP. And let me connect this, the volume VOP here, the first input here. And this is a point VOP. We're processing the points. We're not worrying about the volume. Okay, this is a point VOP, and the second input is a volume. Now, if we dive inside and right click, see there is a volume section here. If we look through this list, there is one called volume sample. This is the same node in the volume VOP, except that we can use it with points in this context. So I'm going to connect the position. I'm going to say use second input. I'm going to connect it to the color to see the result. And look at that. We have color information based on where there is density. Okay, these guys, they are inside the volume and they're returning a value of 1. Everything else is returning a value of something lower than 1 and or 0 here. So let's try and change this name to density. Make sure that we're reading the density attribute. Cool, so we're getting this black and white map. And then the velocity field is named val. So let's change this name to val. When we do that, nothing happens. And the reason for that is because this node here does not know how to sample vector fields. It only works with scalar fields, scalar volume. And the velocity field is a vector field. So we need something else. If we right click, if we hit tab and go back to this volume thing, we see there's a volume sample vector. And this is the node we need to use to sample vector fields from volumes. Let's connect this to the color, change this to val, and this to second input. And look at that, we have the velocity information. And what's happening now is each point is being used, each point position is doing a lookup or a sampling. It's doing a sampling inside the volume, saying, okay, I'm in this position. What is the information? What is the velocity value near me or in that voxel? Okay, so we get that result back. Let's display it as the normal or as the velocity, so we can see the actual vector. Cool, so we can see it there. Let's add a multiply so it's easier to see. And we have the velocity vector. Cool. So let's use this information to offset the points, and all we have to do is take that, the velocity amount, and add it to the position to do the first advection. Okay, I'm gonna add a multiply here to control the amount of velocity, or add a multiplier. I'm gonna set this to 0.1, and let's turn this off. So this is the original position, this is the second position. So we moved these points. Now let's continue doing this. What the trail node is doing, it's repeating this over and over. So I'm gonna, after this advection, this first offset, I'm gonna copy the node. I'm gonna use the offsetted points. After we move them, we're gonna reuse them again to do a second lookup. And so we shift them, they look up a new value, and then we move them again. So let's do this one more time. Every time we use the result from the previous node. Let's do it 5 times. And this is a 5-step advection that we're doing now. And I'm gonna merge all these guys. Select them all. Okay, and see, we have a trail. Let's create an ID or a point number. So ID is equal to point number, so we can trace the points. And we're going to use that attribute with an add node to connect them. So add node polygons by group, by attribute ID, and now we have the trail. Everything else that that didn't move is on top of each other, but there is a primitive. It's just too small to see. There is only a point, and that's the velocity affecting these points. But you can see the graph is not very interesting, and if we wanted to do, let's say, 10 steps or something more, we have to keep adding these nodes, and this is not practical. So what we're going to do is we're going to use a for each loop to do this, and this is not really related to the point lookup. I think the idea is to just learn how to do the sampling, but I want to show you guys how to repeat the process and accumulate the result. So let's say we have some data. We have data D, and then we process that. We have a process. Okay, it generates a new data. ND for new data, and we have a result. Now what if we take this ND and plug it back in as the result? We can repeat this process over and over in a recursive way. So the first time we have an input, we process that, the outcome of this becomes the input, but we don't want just the outcome, we want to also accumulate this. So we're going to add in here, we're going to add a merge node with the previous D, with the previous value. Previous D. And that gets merged. So the first time it goes, nothing here gets merged because this is the first iteration. It processes the data, it generates new data, send it back in, and then we have a copy from the previous D, so we keep that, and then we add it back with a new result after it's been processed. And this way, we start with one point, we apply a process to it, we advect it, let's say, to here, and then that result gets sent back and now we have these 2 points to work with. And that way we can keep progressing through the volume and do lookups and accumulate the result over and over and over. And this is one of the features of the for each loop that we can use it to do this. So I'm going to create a for each, and I want to do a for each number because I want to specify how many times I run this process. I'm going to select the data, which is the inputs, and I'm going to copy this guy. Okay, and this is my input, and this is my second input for the volume. We don't worry about that. And then if we take a look at this, we are seeing the final result. So it runs, at the moment, it runs 10 times, and this is the result. But I don't want to see just the final result of this running 10 times. I want to see it accumulate over and over. So inside this this for each begin to, I'm going to change it from fetch input to fetch feedback. And now it's running the process over and over and over, but it's accumulating the result. And this guy is the time step. Okay, so if I lower this to 0.1, it's going to increase just a tiny bit every time, but we can increase the iteration number to 100. And now we have much more defined curves. But let's set this to 0.05, and let's lower this to 10. Okay, we can increase this as much as we want, and we'll see that continue to do the lookup over and over and over. With one step, nothing happens. The next step, it starts advecting. See, but it kept the points, the previous point. The next iteration, it does the same thing. And every time it uses this new point to do the lookup on the volume. So we're progressing through this entire volume every frame, every step. So let's set this to, let's say, 50. Okay, and we have the thing. Let's do an ID, and now we have the trails. Cool. One thing I want to do is I want to delete the points that did not change. So I'm going to create a rest attribute, and this is actually, I'm not going to create a rest. I'm going to create a new attribute called rest. I'm going to store the current position. That's all. And what I'm going to do is I'm going to, in this result, I'm going to compare if the point has moved compared to its original position. So this is the original position stored, and this is the new location or the new points. I'm going to compare that. So let's create a point VOP. Let's import this rest attribute. So bind, let's import the rest. It's a vector float. And let's subtract the difference between the current position and its original position. I'm going to bind export that as the difference, but I don't want a vector. I want this. I want to compute the length of this. So if the point did not move, its length will be 0. If the point moved, the difference will be higher than 1. So you see here, we have difference, and then if we flip, it's 0. So we can simply delete all the points that have a difference of 0. You can say add difference is equal 0, and make sure it's points, and now we're deleting those points. Okay, now with this advection, we can do the same process inside the pop solver. We've done it here, but let's say we are inside the pop sim, and we emit points, and we want them to look up the volume velocity and get advected or moved by that. So if we have a sim, for example, of the trails or the circle swirling and it's emitting smoke, we can have particles also getting emitted at the same time and tell them to, hey, go sample the velocity from this vector field and move according to that, while respecting that velocity information. And we can do that inside the particle sim using a pop advect by volume. So let me create a pop network. I'm gonna connect these points, And I'm going to connect the second input here. Let's dive inside. I'm going to say emit all points from the first context. And let's go to the first frame. I'm going to say pop advect by volumes. The volume is going to be the second input, and it's called vel. And this node is doing pretty much the same thing that we did. It's using a volume sample. If we look through this, let's see. Yep, it's doing a volume sample field. So it's just running the same operation that we did, but inside the sim. And now see, we're getting the same result, except that this is a sim now, so it keeps moving. And we can add gravity. We can affect these points and have them behave like a sim. Cool. Okay, so now we're going to create a smoke sim for the portal, and we're going to use that to advect some points that we're going to emit. Alright, thank you guys for watching, and see you in the next video. Bye bye.